but I don't have them graded.
What about our exam quiz?
I got none of that. Yes, I'm quite far into grading the binders, but the quiz or the exam. Wait, I already gave the exam back. Yeah. Yeah. Wait a second. D-form. Nope, I haven't started that. Okay, so today, well, a pizza party, that's a good idea.
Yeah.
You've always wondered about first.
We don't have pizza parties on Friday.
First was the thing with rolling down a ramp. Nope.
Oh, we're talking about the Pinewood Derby car today.
That's right. Big day.
That's exciting shit.
Okay, so first was rolling down a ramp. Second was pulleys with masts. And third is Pinewood Derby. Trademark. Trademarked by the Boy Scouts of America.
Is it?
Yes. I'm sure it is, yes.
The name Pinewood Derby?
They're very litigious, Boy Scouts of America.
That's all right. We're such a small organization. How
So-
about we just call it Block of Wood Derby?
Yeah, well, that's how we're going to think about it. So the Pinewood Derby is like this. You have your little wooden car, and you roll it down a hill, and these little kids watch.
You need the stripes on the hat too.
Okay, so this is what we're talking about. Like, and so you make these cars. They come with the body's just a block of wood, and then you carve it and paint it and all this stuff. But we're going to calculate what are the things that that would really affect the motion. We're not going to deal with aerodynamics, which apparently has a small effect, but it can have an effect. Well, we're also not dealing with friction, so the way that whatever has the highest speed when it hits the flat part at the bottom is just, everything's going to keep its speed at the bottom with our model. And so here's the setup. There's no air resistance, so it doesn't matter what the shape is. I don't have a, that's true. I don't have an equation for the style competition. That wheel looks super crooked. No, I always used to draw a lot as a kid. And then I suppose, yeah, you draw a lot of these kind of pictures as a teacher. There's a wheel back there, wheel on the other side back there. So here are the assumptions that we're going to make. The mass of this thing is big M. and each wheel has a mass little m and a moment of inertia about its center, I sub c, and a radius capital R. We want to come up with, so we want an expression for the acceleration let's say the translational acceleration in terms of big M. Oh, no. I said that the mass of this big thing is M. Let's make this 4M. And so we're just going to do a quarter of this problem. But we want the translational acceleration in terms of big M, little m, I sub c, r, and theta, that's the angle of the ramp. The four wheels are just for stability. So the problem we're really going to do is we'll just break this up into a quarter of the problem. Where we just have a quarter of block. We have one wheel. Since this is a quarter of the block, now this is the one with the mass of big M. Yeah, it doesn't work very well. So we'll talk about the interpretation of this at the end. But yeah, you want to bring the whole car for sure. Little m, I sub c, and r. Okay, so that's what we're really doing. And we're just saying that it stays upright. Okay, so to calculate the acceleration, so the acceleration of the translational acceleration of the whole thing is the same as the translational acceleration of the center of the wheel. And so we're going to do a rigid body problem that has to do with the rolling of the wheel. But we also have to deal with the fact, like if we jump right into a free body diagram of the wheel, we'll have a contact force applied to the axle of the wheel by the body of the car that we don't know right now. So I'm going to first isolate the chunk, deal with that as a particle, and come up with an expression for that contact force, and then we'll use that contact force when we go to the wheel. Any questions about why I'm doing that? Nope, I'm just doing the one, and we're just saying it's going to stay up sort of magically. So each of the four wheels is, yeah. Okay, so here's what we have. We're going to use a rotated coordinate system. And the forces acting are a weight force. And this is a free body diagram of the block. So that weight force is big mg. And then we have, since that wheel's connected to the body by a pin joint, we have an unknown force vector. So an unknown X and Y component. I'll call that the force on the block by the wheel. And if you extend this down, this angle is theta. That's the angle of the ramp. We're not doing anything with the orientation of this block, so I'm just going to treat it like a particle. So we'll just go right to Newton's second law. And Newton's second law says F dw x and y plus, now we have to do the trigonometry of that weight force. You could think of that as mg, big MG times cosine and sine of 270 plus theta, but everything will come out neater if we think of the x component as big MG sine theta, and the y component as negative big MG cosine theta. So that's how I'm going to write it. And those are all the forces. So add these up and they're equal to the mass, big M, times the acceleration. We don't know the acceleration yet. That's what we're trying to find. But we do know that it's parallel with the x-axis. So it's not going to sink into the surface or jump off the surface. That is A0. And so the x equation tells us that, well, I'll just write it as, what these give us is that force on the block by the wheel is equal to an x component of big M times the quantity A minus g sine theta. And the y component is big M g cosine theta. Notice that this is a place where statics can give you very bad habits. In statics, if you wanted to calculate the contact force between the wheel and the block, you'd look at this and you'd say the thing that wheel is supporting, that axle is supporting, is the weight of the block. And so you just deal, it would just be the weight of the block acting on that axle. But you can see where that goes wrong here. When it becomes dynamic and you have accelerations, that acceleration comes into this, So your answer would be wrong if you assume that contact force was just supporting the weight.
Well, the contact force is supporting the weight of the block and the wheel.
Well, we're talking about the contact force between the wheel and the block. And if this was static, if it was just sitting there, or if it was moving with a constant velocity, that contact force would just be mg sine theta, mg cosine theta. But you got this A in here because of the dynamics. Okay. And Newton's third law says that then the force on the wheel by the block is the opposite of this. So I'm going to write that as, I guess I'll write it as big M times the quantity g sine theta minus A. And then negative big mg cosine theta. And now we'll go to a free body diagram of the wheel. Well, let me hold off on this for a second. So now we're going to isolate the wheel. And for this, we're going to need to do a rigid body analysis. You can't just treat this as a particle. Because this is rotating. And so let's think of this. Let's go through the steps for a rigid body problem. The first step is we have to figure out whether there's a fixed point or not. Is there a fixed point for the wheel? Yeah, there's not. So our about point needs to be the center of mass. And then 2 is where we calculate the moment of inertia about the center of mass. That's one of the parameters that we're using here. I listed that up above, so the moment of inertia about the center of mass is just I sub c. Now draw a free body diagram. Okay, so there's the circle. The weight acts down like this. The weight of the wheel is little m, or the mass of the wheel. So this is little mg is the weight. Yeah, we are going to use a rotated coordinate system, but no matter what, that's, you know, the weight doesn't care what coordinate system we use. It just does its thing. And then up here we have the force on the wheel by the block. And we know what that is, or we have an expression for it that we're going to use. So that's big M times the quantity, G sine theta minus A. And then for Y, negative big M, G cosine theta. And now go around the boundary of the wheel looking for contact. And there's contact with the ramp. And that contact occurs in 2 ways. There's a normal force. And then there's also a friction force. If there wasn't a friction force, the wheel wouldn't spin. It would just, the thing would slide down like the way it was if this was, you know, if the wheel was rusty and the thing was on grease or whatever. So there's a friction force acting this direction. I'll just call that FF. And this angle again is theta. Let's write out rho, force, moment. Our about point we already chose as the center of mass. We didn't have a choice on that. There's no fixed point. All right, so first let's do the things in the middle at the axle. There's force on the wheel by the block. The row vector from the center to where that force is applied is 0. The force vector is x component big M times the quantity g sine theta minus a. And the y component is negative big M g cosine theta. And there's no moment because that's at the about point. Then there's the weight. That's also acting at the about point, so no row vector. Force vector is positive little m g sine theta, negative little m g cosine theta. Cross product is 0. And the normal force, the row vector is 0, negative r, because that row vector is the vector from the about point to where the force is applied. The force vector is 0, positive n. And so the cross product 0, which makes sense because you could move this normal force along its line of action and put it right there at the center. And then the last force is the friction force. That's also at the location 0, negative r. That's the row vector. And the force vector is in the negative x direction. So the force vector is negative f, 0 for y. Cross product is negative r, f. Anybody have any questions about any of those? Mm-hmm.
Like that's what.
Say it again.
Looking at the force component,
Mm-hmm.
if you forget, like you stop halfway through a problem,
Yeah.
and do something, you can come back and look at those components and know exactly left hand side of what they go.
Oh, yeah.
Uh-huh. And so.
Yeah. Yes. All right, so now that's step 3. Step 4 is Newton's second law. We don't always use that. Do we need it here? Yep. So 4, Newton's second law, and we're doing this because there's no fixed point. So add up the forces. You have the vector big M times the quantity g sine theta minus a. And the y component is negative big M g cosine theta. And then the weight of the wheel, little mg sine theta, negative little mg cosine theta. And then the normal force, 0n, and the friction force, negative f, 0. And all that's equal to a mass times acceleration. What's the point that we need the acceleration at for this equation? Yeah, and so So how does that relate to the acceleration that we already have? That's something you have to be real careful with. In this case, if you weren't careful, you'd be lucky. But you know, remember that the center of this wheel is connected to the axle, and the axle is connected to the block. So the acceleration of the center of mass of the wheel is the acceleration of the block. Okay, that doesn't necessarily have to be true, but that's how it is here. So this is all equal to the mass of the object we're isolating, little m, times the acceleration vector of the block, ma. Well, if this wasn't rolling, this was like an arm or something in a machine, okay, then this would, that pin would be at one end of the arm, yep. and so you'd have to deal with the fact that those accelerations are different. Okay. Okay, so what do we get here? The only equation here that's going to be useful is let's keep going in order, but the y equation isn't going to be useful to us. We're not trying to calculate that normal force or anything like that. So the x equation is the one that we're gonna go on with. But step 5, the moment equation. There's only one force that produces a moment. And so this equation says negative r times the force of friction is equal to the moment of inertia about our, around our about point, and that is IC, times the angular acceleration. Okay, so we got those two equations from Newton's second law for the block, but we already used all that information here. So we've already dealt with equations, those first two equations from Newton's second law. The only equations we're working with at this point are the ones coming from isolating the wheel. Okay. So let's think about what we have. We don't care about n, so I'm going to leave that equation out. So we have these two equations. The first one says big M times the quantity g sine theta minus a, and then plus little mg sine theta minus ff is equal to little m a. And then the second useful equation, we're skipping the y equation, comes from the moment equation, and that says negative r f f is equal to I sub c alpha. Okay, so here is our system of equations. And if we can solve this, we're done.
For the day?
Yeah, done for the day. Really? I mean, you might want to do other stuff today, but this class is done for the day, if we can solve this. But we can't. Because, so let's think about variables, because we got a lot of, I was in a class, like a calculus class in college, and the professor derives some big thing like that, and this woman in the back was like, so we get alphabet soup. Well, what does it mean? And it was the craziest thing that's ever happened to me in my life, I think. Like, I'll never forget it. So, don't, yeah, just in rage. So first, try not to ever be that person. But second, like, let's make sense out of what all this stuff means. Um, right now, it's just alphabet soup. So we have to separate this into what to us are the variables, the things we're trying to find, and what to us are the constants that we're trying to get this in terms of. Okay, there's a lot of letters, and some we're assuming are treating like we know, and some we're trying to solve for. So the things that are parameters that we're not trying to solve for, we're solving in terms of are big M and little m, G, theta, R, and I sub C. Okay. The things that we're trying to solve for, the variables are A, force of friction, that's A again, and alpha. Yep. So we have two equations, but three unknowns. And the three unknowns are A, FF, and alpha. So we can't solve it yet. What are we going to do? Of what? Yeah, well, we're assuming, so we're going to get an answer that has big M and little m built into it. And then you could weigh your Pinewood Derby car and fill those in, you know. Yes, that's right. That's right. That's right. So, right, we need a constraint equation. Where's that going to come from? Yeah, so it's rolling without slipping. So the constraint equation comes from rolling without slipping. And that says that the total acceleration of the center of a wheel is equal to, for the x component, negative r alpha and 0 for the y component. And our expression for the acceleration of the center is this variable a and then 0. So there's two equations. One says 0 equals 0, so that doesn't help. The other one says that, well, I'll write it as alpha is equal to negative a over r. And now we're going to take this equation and substitute it into the first two equations. That'll eliminate alpha, and then we have two equations for two unknowns. So we'll rewrite the system. The first equation says, I'm going to break up that big term into, so we have big M, G sine theta, minus big M A, plus little m G sine theta, minus FF is equal to little m A. And then the second equation, this is where we'll make the substitution, says negative RFF is equal to negative I sub C over R times A. And now this is two equations for two variables. So the second one tells us that the force of friction is equal to negative I sub c over r squared times A. Yes. And so substitute that in, and you get big mg sine theta minus big MA plus little mg sine theta minus I sub c over r squared times A is equal to little m A. And now we can move all the stuff with A's over to the right side. We get big mg sine theta plus little mg sine theta is equal to A times the quantity, big M, plus little m, plus I sub c over r squared. And now we can come up with the final expression for A, divide both sides by the stuff in parentheses. I'll group this together. So we have the quantity big M plus little m, all times g sine theta, divided by big M plus little m plus the quantity IC over r squared. And that's the deal. No, everything, the axle and the car and everything, they all have the same acceleration. That's a single rigid body that's not rotating or anything. So if you wanted, so what we did is we assumed that all four of those wheels, the chunk of block with its corresponding wheel, they're all doing the same thing. So if we can break it into one piece, calculate the acceleration for that, we have the acceleration for the whole thing. But what you do have to do is remember that when you weigh the block, the main body of the car, you have to divide it by 4 to get the big M that you're using here. Okay, so what does this say? Let's. Big M is 1/4 of the mass just of the block, the body. Yeah. Right. The axle is part of the body. Yeah. So weigh your nails when you weigh the body. Yeah. Yeah, sand them first. Yes. Yeah. All right, and remember that for most round shapes, we can represent the mass moment of inertia about the center as some constant times the mass times the radius squared. And so in that case, you could think of this as A being equal to the quantity big M plus little m times g sine theta divided by big M plus little m plus this Cm. Yes, that's right. Yeah, because that's the moment of inertia for the wheel. Yeah. C is just some constant. So for a disk, C would be 1/2. For a sphere, C would be 2/5. Well, these wheels, I don't know what it would be. This is something greater than 0. So a cross section of the wheels looks like this. Here's the axle. And so, you could calculate what that is by calculating the moment of inertia of this as a disk. This is a ring. This is a disk. And then adding all the moments of inertia together. Yeah, that's sliced down the middle, looking at the car like as it's coming towards you. So what this says is, nope. Right, but they probably often don't inspect very closely. So that's what we're.
So it means you can cheat.
Yeah, so I would say if you wanted to cheat, I mean they're totally standardized, but yeah, if you wanted to cheat, you take this and hold it up to some kind of like sanding thing, and just sand this down half of the way or a quarter of the way, especially the outer one because that's the mass that's the farthest from the center of mass. So if you cut that down, a significant amount, it would make a big difference. What? What are those? Oh yeah. Okay. I was thinking of a checkerboard. Okay, checkers, right? Well, they would notice that more quickly than they would notice you sanding that. Yeah. Oh my God, you can't believe how long the list of rules is for this. It's all so specific. They give you the whole package, yeah.
Anything used outside of that is not considered okay.
Yeah. So the friction, if you sand down that axle, it's a nail. If you sand it down and then put graphite paste or whatever it's called, like lube inside there, the friction is very low. So making the friction less isn't going to help you very much, but you can. The thing is, if you sand this down, this down, this down, you're going to make that C smaller. And if you make that C smaller, obviously if the denominator gets smaller, the acceleration is going to get bigger. You can also, you can make the acceleration bigger by keeping m constant, little m constant, and making big M bigger. So if you keep the same wheels and keep increasing the mass on the main body, it accelerates more. Well, they've already in the rules there's a limit. I think it's 500. I don't remember. There's some gram limit for how heavy the whole thing can be. Yep. I can't think of a case where it would be one. I can't think of a case where um, that doesn't really have a super clear like physical meaning. But if you had I think if you had a wheel that, so if this thing was big and you didn't have these outer flanges or whatever you call those, and then this had a ton of mass concentrated right next to the axle, you'd probably get a value that got higher than 1/2 or whatever. But I'm just using this C notation because this is a form that keeps coming up for these. And then, okay, so you can't go over the fixed maximum mass for M. You can't sand down the wheels, but but then the one thing that they do let you do, the one thing that they do let you do is they let you lift one of those wheels up so it doesn't ever touch the ground. And basically what that does is, we started with a mass of the body of 4m, and then we divided it by 4 for each wheel. Well, if you only have 3 wheels touching the ground, you're dividing that 4m by 3. So now your big M is 4/3 M, and you have this same equation, except your big M is bigger relative to everything else, and it makes a pretty big difference. Okay, I guess that's all I wanted to say about it. Anybody have any questions about that? Yeah, anybody want to come back and do an oral report on the rules for Pinewood Derby?
It can be 2 3/4 wide, 7 long, not over 5 ounces. Lift between the wheels. These are like the rules in the box.
Mm-hmm.
Must be made during the current year. Wheel bearings, washers, and bushings are prohibited. Not ride on springs. Only official Cub Scout Grand Prix Pinewood Derby wheels.
Yeah.
Only dry lubricant is permitted.
Yeah, so the little graphite squirt stuff. Yeah. 3 is the minimum.
Barely off,
Mhm.
perfectly.
Yeah.
Yeah, I don't think they actually specify how many wheels. It's just
I thought they did, but. Mhm. Yeah. Oh. Mhm.